Um, Welcome everyone. So we are going to start today's video with set of questions. Let's begin. Later in this video, we are going to also discuss the idea of degrees of freedom. That how a monatomic gas has 3 degrees of freedom. For diatomic gas, it is 5, and so on. Then we are going to discuss the idea of law of equipartition of energy. So it is a key idea in basically uh, the internal energy of a gas. We say that from that law, we are able to say that the internal energy of a gas is the integral multiple of some value half kT. So how is that? How were we able to say that thing? So, so first of all, we are going to start with some questions. So that will basically keep us excited. So let's begin. So the first question is we have 5 moles of oxygen uh, and it is heated at constant volume from 10 degrees Celsius to 20 degrees Celsius. So change in temperature is from 10 degrees Celsius to 20 degrees Celsius. Now we are to say that if this is the change in temperature of the oxygen gas, and oxygen has a symbol of O2 and we have 5 moles of oxygen. Okay. So uh, question is what is the change in internal energy of the gas? So what do we mean by that? What is the change in internal energy of a gas? So we discussed that the internal energy of the gas is its kinetic energy. The kinetic energy of the gas is by virtue of its motion in the gas particles. So, how fast the particles are moving with respect to gas containers? How fast are particles rotating about their axis? Decide their kinetic energy. Now, there are other energies involved as well, like the interaction between two particles. So, we know that when there are two ions placed close to each other, they will have electrostatic attraction or electrostatic repulsion between them. So this is a non-zero force, but we say that this force is negligible when intermolecular distances between the atoms is high. So the only force which is the internal energy of the gas is the kinetic energy. So that means that internal energy of the gas is nothing but the kinetic energy of the gas at T temperature. Now this is true for a monatomic gas, like I said. So for a let's say a gas with F degree of freedom, this was this will be F by 2 RT. So the change in internal energy of dioxygen if its temperature is changed from 10 to 20 is equal to F by 2 R delta T into moles of the gas as well. So that's it. Now, what is the degree of freedom of a diatomic molecule? So I said that we'll discuss later, but for now, we know that degree of freedom for diatomic particles is 5. So we'll just put that value here. We'll get 5 by 2 into universal gas constant. So we are given this whole value actually, 5R by 2. This value is given to us as 6 calorie per mole per degree Celsius or Kelvin. Okay. Now this value, may not be visible clearly because of high reflection, but this value is 6. It is given in the question that this whole value 5R by 2 is 6 calorie per mole per degree Celsius. So if you have to just multiply it with the moles of the gas, that is 5, and the change in temperature, that is 10. So it comes out to be 6 times 5 times 10, that is 300 calories. So that means that the change in internal energy of the gas as its temperature changes from 10 degrees Celsius to 20 degrees Celsius, if it's a dioxygen gas, is 300 calories. So I would like to summarize uh, this question. Basically, we were asked to find what is the change in internal energy of a gas. So our response was that uh, what is the change in internal energy? So internal energy of a ideal gas is nothing but its kinetic energy. That is the total kinetic energy. So total kinetic energy comprises of translational kinetic energy and rotational kinetic energy. When we do that for a diatomic gas, then that factor becomes 5R by 2 or FR by 2. So that value FR by 2 is already given to us. That was 6 calorie per mole per degree Celsius. So we just had to say that, okay, uh, what do we multiply it with? So we multiply it with the change in temperature of the gas and the moles of the gas. So that gives us now. Next question we have an ideal. uh, So we have an ideal monatomic gas at T is equal to 27 degrees Celsius and pressure 10 to the power 6 pascals. It occupies 10-liter volume. 10 kilocalorie heat is added to the system without changing the volume. So in the previous question also, when we added heat to the system, the volume was constant. So uh, here as well, we are saying the same thing, that when heat is added to the system, there is no change in volume. What is the final temperature of the gas if Cv is equal to 3 calorie per mole Kelvin? So again, uh, we are basically looking at the same thing. We have to find what is the heat added to the system, uh, or we are given the heat added in the system, and we are supposed to find something. So we did a definition in the last lecture, which was the heat added to the system per unit mole of gas per unit rise in temperature at constant volume is nothing but this factor Cv. From this only, we are able to say that heat is equal to NCV, change in temperature. So now basically this whole value, that is the heat which we are adding to the system. Uh, this value only was what was given in the previous question, Cv. So you can learn that this Cv is equal to F into R by 2. So this is the change in internal energy of the gas. Okay. So what heat we have added? Moles of the gas is uh, we are given the basically the temperature, pressure, and volume of the gas. So this NCV delta T we can figure out using uh, the equation or the moles of the gas. We can figure out using PV equal to nRT equation, right? We can say pressure volume upon RT is equal to N. So we can put that value here. That value will be PV upon RT. Now here what would be T? It should be the initial temperature Ti. So let's mark it as Ti into the uh, specific heat of the gas at constant volume, that is 3, into the change in temperature, that is the final temperature minus the initial temperature. So this is the equation which we have. So what basically are our background thinking about this question? As such, in the face of it, this question is pretty simple. We have a uh, formula which we have to use, and we have to basically uh, put the values of moles. So moles we didn't have, so that's why we used the ideal gas equation. So basically, this is what we have to keep in mind, uh, and that is also some kind of difficulty which is added into the question. Not all questions are absolutely straightforward, as was the previous one. Um, in the previous question, we had moles of the gas. We were given what is Fr by 2. We were given what is change in temperature, and we just had to plug on those values. So there was not much in it. But sometimes question can come which need you to think what is the additional equation required. So we'll put that value, the heat given to the question, or heat given to the question, or the gas, 10 kilocal of heat is F. So this is 10 to the power 4 calories of heat. is equal to P into V. So pressure of the gas is 10 to the power 6. Uh, the value of volume is 10 liters. So 1 liter is 1 decimeter cube. So we'll say this is 10 to the power minus 3 meter cube into 10 liters. This was 10 liters. 10 liters multiplied by 10 to the power minus 3. Uh, Divided by R, universal gas constant. So value of R is 8.31, we can say. This is 8.3. Value of the heat which we are given is in calories, so we have to convert it into joules. So this is 4.2. Initial temperature is 300 kelvins, and this is basically what we are figuring out. TF minus 27 degrees Celsius. Yes, calculate the final temperature of the gas. So I'll explain what I have written. We were given the pressure of the gas. So pressure of the gas was 10 to the power 6, that we have written. We were given the volume of the gas, that was 10 liter. We have converted into meter cube. We are given the heat supplied to the gas. We have converted from calories to joules. Hmm. And we have also the temperature of the gas. That is 300 Kelvin. So 300 Kelvin times 8.3, that is the uh, universal gas constant. Yes, please. Now we have to calculate. So this is 10 to the power 3 into 10 to the power 1. So this is 10 to the power 4. 10 to the power 4 and 10 to the power 4 cancel. So this is 4.2 times 8.3 times 300 is equal to TF minus 27. So I think we have to divide this by 4.2. This is, yes, calories, 10 to the power 4 calories. So 4.2 calorie is 1 joule. So that means 10 to the power 4 calories is this much divided by 4.2. So we have a dividing factor of 4.2 here. This approximately goes out to 2 only. 4.2 divided by 8, 8.3 divided by 4.2 is 2 only. So this is 600. So fine. Uh, so this is the final answer. That is, again, it is not visible because of reflection. So the final answer is 600 plus 27, that is 627 degrees Celsius. Next question. We have 0.3 grams of oxygen. It is kept in a rigid container and is heated. So again, it's a constant volume process. So Like we were learning from the starting only कि the internal energy of the gas is nothing but its kinetic energy, right? Uh, and what is the total kinetic energy of a gas? Total kinetic energy of the gas is F by 2 into RT. So that becomes the internal energy of the gas. And that internal energy of the gas is also equal to NCV delta T, where CV is the heat supplied at constant volume. So this is what we have established up till now. Now let us see how again this concept comes up. That whatever heat which we are supplying goes into that total kinetic energy of the gas. So 0.32 grams of oxygen is kept in a rigid container and is heated, right? Heated, that means heat is supplied. Find the amount of heat needed to rise the temperature from 25 degrees Celsius to 35 for this gas if it is given that the molar heat capacity of oxygen is 20 joules per mole per Kelvin. So again, we are given CV. CV is 20. So if we divide the total mass of the gas by the molar mass, we'll get this much moles. So the moles of the gas is 10 to the power minus 2 moles. Okay. Heat supplied to the system is equal to NCV delta T. So that is the point. N is. And what is the change in temperature? Change is temperatures from so this is some 2 joules. It's a rather easy calculation. Everything we have. Next question. Again, we have 1 mole of a monatomic gas. This is rather a good one. So we are mixing two kinds of gases. 1 mole of a monatomic gas. It is mixed with 3 moles of a diatomic gas. So we have 1 mole of a monatomic gas and 3 mole of a diatomic gas. Uh, what is the molar specific heat of the mixture at constant pressure? Okay. So first of all, we need to know what is the molar specific heat of gas uh, for the monatomic gas and the diatomic gas. That's how should we approach a question. In any question, first we need to figure out what we already know. From that only we must get to that critical step. That okay, this is the point where I'm going to get stuck at the question. I do not know, okay, what is the formula to find the mixture, uh, the specific heat of the gas. What is the that formula for the mixture of a gas, and that too at constant pressure. So how would I do that? So first we know this is the molar specific heat of gas at constant pressure. So we can just put the value of F for each of the gases. I'll say this is 1 plus monatomic gas 3 by 2 into R. And for the other gas, I'll write that as Cp dash. For a monatomic gas, let's say Cp is Cp dash. Diatomic gas, it is Cp double dash. Okay, so that we can figure out. I hope it is visible. Uh, it is Cp dash and this is Cp double dash. So again, using this formula, it will be for diatomic gas, it is 5 by 2 into R. So this is 1 plus 5 by 2 into R. So this values and this values. So the idea is what will happen to the gas if I'm supplying some heat to it when they are mixed. The molecules of the gas, they will absorb this energy. So would one gas get more energy, or whether the other gas would get more energy, or would both the gases get equal energy? We know there would be something at play. So the point is that when the gases they get energy, they get it in proportion of their molar specific heats. And what is basically the number of molecules of that gas? It is as simple as that. If the gas has more molecules, it will get more fraction of that energy. If the gas has more specific heat of gas, then it requires more heat to get that 1 degree Celsius rise in temperature. So that means that if we are supplying some heat Q, it will be divided into gas like this, Q1 plus Q2, right? Thinking in simple terms, the heat is not going to be everywhere. Now, if this gas was alone in the uh, chamber, then we would say the heat given is the heat what we have given to the gas is Q1, so it will be Cv dash into delta T plus, now if this gas was there, then Cv double dash into delta T, and the moles of the gas would be also I have marked. Now, moles of gas number 1 is N dash. Specific heat of gas number 2 is Cv dash. Moles of gas 2 is N double dash. Specific heat of gas number 2 is Cv double dash. One mistake I have done is we have to take specific heat at constant pressure. So we'll take Cp and here as well. Uh, Now I'll say the total heat supply will be uh, distributed like this. And what if it were a single gas? Then I'll say if it were a single gas, from this point we have to make a now we have to think that okay, what is required in the question? What is required in the question is molar specific heat for the combined mixture. So now we think it as a single gas. It has a single G. This is moles of gas 1 plus moles of gas number 2 into molar specific heat of the gas at constant pressure into the change in temperature. That's it. Now we equate these two values. If I equate these two values, I'll simply get n dash Cp dash plus n dash Cp double dash into delta T is equal to n dash plus n double dash into Cp into delta T. That delta T I have cleverly already cancelled out, so I get to write one step less. And Cp. Now n dash Cp dash plus n dash Cp double dash divided by n dash plus n dash. This is my molar specific heat for the mixture. Now we'll just put the values. Moles of gas number 1 is 1. So 1 into 5R by 2 plus 3 into that for diatomic gas 3R by 2 plus 1 plus 3. If I combine these two values, this is 14. Now we want to discuss the idea which we had. So thank you for joining.